All right, so in this one, we're going to jump into chapter 4 and we're going to start talking about more things we're going to do with the derivatives. So you see here the title, Graphing and Optimization. We're talking about first derivatives, which we've already done, but we're going to use this information to help graph our more complicated equations. So like always, I'm just going to jump in here and start with these slides and then kind of get you an idea of where we're going to go with this and then do some homework problems as well. So there's a number of slides here. If you can't really tell yet, but there are 35 slides. So I'm not going to go through every one of them. Some of them I'm going to go through a little bit faster. But like I said, like always, I want to spend as much time with the homework as possible. Okay, so we already know the derivative has to do with the slope of the line, a tangent line. It also is basically talking about the slope of the graph. Okay, so as we have a graph that's moving upward, it's going to have a positive slope. A graph that's trending downward, it's going to have a negative slope. So that's what we have. So we're going to talk about other properties here. And the interesting thing is, like I said, it's going to refine our picture. All right, it's going to talk about important things. And a lot of it is going to be maximums, minimums, where things are going up and down, all these different things. But the main part with the first derivative is talking about that. So they talk about these sign charts. Now, some people like these, some people don't. They're going to use them a lot in this chapter. I tend to use them. It's not absolutely required, but we're going to be talking about those. We're going to use these to try to illustrate where we're going. Okay, so show you here what's going on. We have this function, f of x equals x cubed minus 3x. We have the derivative, reading a couple of things here, which is 3x squared minus 3. And notice what they've done is they've kind of expanded this. I like to go downward. I don't like to write sideways here. But what they did was they factored out a 3. So it gives you a 3 times, if I can write that, 3 times x squared minus 1. And then that breaks down the difference of two squares to x plus 1, x minus 1. So that's how they ended up with this piece right here, just so you're clear where this is coming from. All right? So what we're going to do next is, by looking at that derivative, we're able to tell, okay, this sign chart stuff, and we're going to talk about this here, we're able to tell where our graph is going upward, where it's going downward, and where it's going upward again. Wherever our graph changes directions or does any kind of behavior, the derivative is going to tell us all of this. So this sign chart, I'm going to get to this, how we do this in a second here, but when you look from left to right, okay, just imagine you're traveling in a car that's going up the hill, down the hill, up the hill. What's going on? Because a lot of people say, well, this is going up and it's going down, depending where you're coming from. So just remember, from left to right, what's the behavior of the graph? So as you see here, and like I said, we've already jumped ahead showing the picture, but they're giving you a demonstration. As we go from left to right, notice we're going uphill this entire time. Then as soon as we reach the top of this hill, now we're falling downhill until we reach the bottom of that valley, and then we turn around and we're going back uphill again. That's the derivative is going to help tell us all of this information. Okay, and you'll see why in a second where all this is coming from. But that's what's going on when we talk about this behavior. We're going to do a sign chart. The sign chart is essentially based on this. So if you've done this before, this is going to be familiar. If not, it's going to take a couple steps, but you'll figure out. What we do first is, when we have a derivative, let's see if I have room right here. Our derivative is equal to this. Now our first step, and you'll see this in more detail in the next few slides, is we want to first set this thing equal to 0. Okay, that's the key. When you set it equal to 0, we get an x equals negative 1. We get an x equals positive 1. What that's going to tell you, I'm going to call these critical points. Okay, they're important things that are going on here, and you'll learn in the future. That's how you know the maxes and the minimums. The peaks and the valleys of your graph are always going to have slopes of 0. The tangent lines are, as you can see, the ones I'm writing right here and here. That tells you where your high and low points are. They call them the relative maximums and relative mins. That's what you know is happening at negative 1 with this one, and at positive 1 with that one. Again, we're talking about the x values. At x is 1 and x is negative 1, that's when you're getting these maxes and these mins. Okay, so now jump forward a second. like I said, pretend you only have this equation. What's going to happen is you're going to be able to tell where the graph is increasing and decreasing and where the peaks and valleys are when everything's going on all from this derivative. So once we have these critical points, I know I erased them, but we have our critical points at -1 and +1. What we want to figure out is what's happening in each of these regions. So you're going to take this derivative that we've just found, and you're going to test points in every one of these regions. So I'm going to pick a point like x equals 0 here. I'm going to pick a point like x equals 2. Here I'll pick a point like x is -2. And I'm just testing what happens when you plug each of those into this entire derivative. So start with the easy one. When you plug in 0 to this equation right here, to this bit, what do you get? You get 3 times 1 times -1. I don't really care about the number, I just care about the sign. I get a negative. That tells me my graph is decreasing there in that area. And it doesn't have to be the middle point that I pick. I can pick any point between 1 and -1 right there. I just pick the easiest one. I know that every single point here is decreasing. The function is decreasing right there. So I turn around and do the same thing here with the 2. When I plug in 2 to this derivative, I get 3 times 3 times 1. All I'm looking at is the signs. It's a positive number, which tells me in this area over here, my function is increasing. Now, some of you may wonder, well, maybe we got lucky. We picked the number 2, and that was a positive slope. What if I picked another number? Believe me, you can pick any number in there. And the rule is, because we have a 0 right here, we have a slope of 0 at this 1, every single value here is going to have the same slope, whether it's, as in the sign, whether it's positive or negative. Same thing right here. We have a couple of zeros. If one of these gives you a slope that's a negative, a derivative that's a negative, every one of them will be, because we have learned these old rules before. You can't jump from a negative to a positive when these are my only zeros right here. And lastly, I'll take another test point. Like I said, I'll test -2. And when you plug in -2, you get 3 times -1 times -3. You get a positive times a negative. That's a positive. So my function is increasing in this area as well. And this correlates to the picture that you see right here. Assuming we didn't know the picture, we're going to use this information to help get a better picture. Okay, so that's the quick version of what we're going to do. And like I said, I'll pull up these slides and you kind of see what's going on. You see by the graph here, we know it's from left to right, it's going to be positive in those regions, and the interval of the graph is going negative, where it's decreasing, is going to be that middle one right there. Sorry, I'm erasing while I'm having this animation go. But that's kind of the summary, how we know what's going on. By testing the derivative, we can figure this out. So we know the derivative is 0 there, and those are those 2 points right there. All this is from looking at that derivative, that original derivative we found, the factor form right there, and just testing different points to see what you get. Okay? So, see some more examples here. So, for that function right there, it's increasing when the derivative is greater than 0. It's decreasing when the derivative is less than 0. So rising and falling. And they give some examples of how your graph may look. So you look at this, here's a straight line that we're used to on the far right. Of course, we know this is an increasing graph, again, from left to right. But this one right here, if I get a graph that looks like this, it may not look like it because it's kind of tapering off. But technically, this is an uphill. It's going upward, upward, upward. Even though it may get flat, it's still slightly rising. So that's considered increasing. Just like the reverse here, that one's increasing. So these are types of graphs you may see. And we'll refine these as we get more information about our function. So here's when you're decreasing a negative slope, you get these kind of graphs. All those are decreasing. So just examples of how your graph will look when your derivative is either positive or negative. So now the question here on this graph, which values of x correspond to horizontal tangent lines? So just to give you an idea, If I have a graph like this, and I'm going to draw a bunch of tangent lines, here's one, here's one, here's one, here's one, and we want to know where do we get these horizontal tangent lines. So as I mentioned a minute ago, horizontal tangent lines happen at the peaks and the valleys of your graph, the relative maximums and minimums. The way we do that is we're going to take that derivative of this function first, and then we're going to set it equal to 0. So that's what that's our process. Oops, sorry. So you find the derivative, you solve with the derivative equal to 0, and then you see what x values you get. So again, not forgetting, we know how to find our derivative right here. We've done that. Now, I don't like this. My approach is I put a 0 right there, and I set the derivative equal to 0. It doesn't matter though. Either way, as long as you make this quantity right here equal to 0, and then of course when you solve it, you get a 2x equals 8, x equals 4, and that's saying you're going to have one place on this graph where you're going to get a maximum or a minimum, where you're going to get a horizontal tangent line, and that's when x equals 4. Okay? So right there at x equals 4. So now they want you to figure out where the graph is increasing or decreasing. So we're going to assume that we've already found the x equals 4, and you look at what we have right now. They don't give a whole lot of information, so let me kind of add some details right here. Since we know that 4 is a special point, that's our critical value. Remember where the derivative is equal to 0? I want to test both sides. And the good news is you only have to test one point. So I'm going to test right here in the derivative, and it could be in this derivative. Oh, sorry, not that. That's not my derivative. Let me go back. I erased the derivative. I'm sorry. The derivative is 8 minus 2x. So I want to test into here. So, for example, let's test the point 0. So I'm going to go find f prime of 0, and I get 8 minus 0. I get an 8. All I care about is this is positive, so this region here is going to be positive. And like I said, you could pick any number. You can't pick the 4, but any number to the left of 4. I could pick 3. I could pick 3.9. I could pick negative 17. Any number to the left of 4 covers that entire region. Now we're going to test another number. Let's test 5. When I find f, it's supposed to be f prime of 5. I again plug 5 into that derivative above, and all I'm looking at is I get a negative, so I get a negative here. So that tells me that of these two graphs, it's going to be increasing on the up to 4, and then as soon as you hit 4, it's going to be decreasing. So that's how they're able to come to the conclusion of where this graph, they didn't show all this work, but that's what's happening. Okay? So to kind of clarify what's going on, so it's, we're looking at all this right here. They did the inequalities. I'm not a big fan of that, but it does work. It does just the same thing here. They say, well, let's figure out where x is greater than 0, where this whole function, is greater than 0. You solve that, and you figure out it's x is less than 4. So that tells you all the places greater than 0 is all the places it's increasing. And then, same thing here, let's find out where it's decreasing. We take that entire derivative, set it less than 0. Okay? It works good when you have nice, simple functions like this. When you start getting powers here, it does become a problem. So that's why I always revert to the testing of the regions. Either way is going to work, but this is the way that we can tell. Without even looking at our picture, we know where the graph is having a tangent line with a horizontal tangent line. We know where our graph is increasing, where it's decreasing. So now, I want to summarize what we've learned. We know there's a horizontal tangent line at 4, which tells us that's going to be a maximum or a minimum. So, kind of leading up to this, when we're at 4, we know that's going to be a max or a min. I don't know yet, okay? But if we know our graph is increasing over here and it's decreasing over here, just think about that. Well, the graph has to go up, 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 then it hits 4, and then it's going to go down, down, down. That tells me this is going to be a maximum point of some kind. And it's probably one of the more important points. All these highs and lows are always important. So if I want to get the actual coordinate of that, I'm going to go back to the original graph and I'm going to plug in 4. Because remember, when you plug in a point, an x to the derivative, you get the slope. When you plug it into the original, you're getting the actual point, like we learned from the very beginning. So when I plug it into here, I get 32 minus 16. I get a 16. So that tells me this is a maximum. Not only do I know it's at 4, I know it's at 4 comma 16. I know the actual coordinate of that high point. So then remember, our graph is increasing, then it's decreasing, and you know what graphs look like that. And remember, this is a square graph. This is a parabola. This is going to be an upside down parabola. That's what we have here. So I'm going to erase all this and just kind of show you what I have. We get this graph right here. At the point 4 comma 16 is your maximum with a horizontal tangent line. You don't need the horizontal tangent line, but just to show you that's the importance. And it's increasing, 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 and then it hits it, and it's reached the top of the mountain. Now it's decreasing, decreasing. And we know all these bits of information before we even get to the picture. Now, did you need to do that for a square function? You might know how to graph that already. It's a parabola. Same with a cube. You might know how to do those. But when you get to powers of 4 or 5, 6, or fractions or other weird things, these important facts are really going to help you out so that you're not just randomly picking points. You're going to know definitive traits of every picture we have. Okay, so we talk about things, talk about the domain. If you have a real number x in the domain such that the derivative of that is 0, or if it doesn't exist, it's known as a critical number. All right, so we'll talk about derivatives that don't exist in a minute, but for now, let's start with what I talked about earlier. Anytime you get an x value that gives you a 0 derivative, a horizontal slope, that's going to be a critical number. Now later on, we're going to learn that there are places in the derivative that doesn't exist, whether it's an asymptote or just a hole or dotted line, that's also going to be considered a critical number. Okay, so they're important to know here. And this partitioning, you'll see this sign chart, this is what I was doing earlier. Okay, when we talk about the sign chart. So let's get to an example right here. We have a function, f of x equals 1 plus x cubed. We want to know where it's increasing and decreasing in this. So first step, find the derivative. All right, so I find the derivative, which is a 3x squared. I set it equal to 0, and I get one critical number. I get a 0 right there. Now remember that other stuff is where does x not exist? What you need to find and get used to is, and they won't always show that here, but they'll talk about it in a second. When you have this derivative right here, you also want to immediately in your head or write it down, ask yourself, what's the domain of that derivative? Okay? We need to know the domain of the function too, but the derivative is a very important one as well, because sometimes when you take a derivative, points that may have existed earlier, they disappear. Okay, and you'll see lots of examples of these. We just want to see the domain. Well, when I look at 3x squared, all real numbers will work. Every number is going to work, so I don't have to worry about anything. But if there was, for example, if you check the domain and you found, oh yeah, I cannot have it equal to 2, what that translates to is, that's going to be another critical number. If that point doesn't exist, it's going to have a part in our next step. Okay, but if you get all real numbers, you just skip that part and we say to ourselves, okay, we only have one critical number. It's going to be here at 0. Oops, sorry about that. Okay, so our only critical number is 0, as I just mentioned. All right, so now we're going to do a sign chart. Just that was what I was doing a second ago. Remember, we take our critical number, which is at 0, and we're going to test both sides of the critical number. Okay, we know at 0 it's going to have a 0 horizontal slope of the tangent line, but we want to check both sides. So if we check the left, pick a number, -1, -2, anything. When you plug it into the derivative, you're going to find 3x squared, you get a positive number. That means we're increasing here on the left. Now earlier we were increasing, decreasing, we were alternating, but don't always assume that, because when you plug in a number like 1, 2, or 3 here,
into the derivative, you also get a positive. So what that means is our function is increasing until it hits 0, then it increases some more. Okay, so you might be wondering, how in the world can you have that? You'll see in a second, but it's increasing all the way up to 0 and everything after 0, but not including 0 itself, because technically it's sort of frozen there at 0. All right, so show you, okay, they didn't show the picture, but just to kind of point out, I'll graph this real quick. What this is an example of this function right here, our cube function. But what happens is, if I draw my tangent lines, here's a tangent line, tangent line, tangent line, and for a split second, we have a horizontal tangent line right here, and then it goes back to more positives. So that's a case of your graph continues to increase. It slightly pauses at x equals 0, and then it picks right back up again. But it never goes downward like that. It just goes up, pauses for a second, and then continues up. That's a case of increasing everywhere except for one spot where it's a 0. Okay, now we start getting to the fun ones that you cannot normally do, or I don't want to say you cannot, but we don't normally graph these, or at least very easily. Now we're going to learn characteristics about this. Even though it's an ugly power, the rules still apply. Now my first thing to ask is, what's the domain of this? Okay, now they're not going to talk about it yet, but I want you all to be clear. Remember, what this means is, this is the cube root of 1 minus x. So what's the domain? Well, if that was a square root, we'd have to worry about negative numbers inside that quantity, but because it's a cube root, I can put anything in there. I can put a 0 in here, I can have this whole thing 0, I can have it negative. Everything works. So let me just kind of put up here, my domain is all real numbers. A little symbol for all real numbers. Okay, so we don't have anything to worry about on that one. That's just, remember, that's of the actual graph. So if my graph has all real numbers, there's going to be a point everywhere. I just want to know where it's increasing, decreasing, maxes, mins, all that good stuff. So we're going to go right in the derivative. Okay, so let's quick reminder of what our derivative is. We have a 1/3 times the parenthesis, and we have a negative 2/3. Okay, so remember where we get this from. The 1/3 is multiplied out front, and the power was we decrease our power by 1, so 1/3 minus 1 is negative 2/3. Now if you notice, there's a negative out here. Why is there a negative here? Do you remember? There's the chain rule. Okay, we did the power rule, 1/3 and negative 2/3, but remember the chain rule says we have to multiply by the derivative of the inside, and the derivative of the inside was a negative 1. That's why there's a negative out here, and multiply to the whole thing. So then they clean it up. They bring this down because a negative power means the same thing as putting on the bottom. We get negative 1 over 3 parenthesis 1 minus x to the 2/3. This is our derivative right here. Okay, so I want to highlight this just so we're aware. That is my all-important derivative for our next couple steps that we're going to be doing. Okay, now, so before we go on, couple things. We have to look at what the domain is of this. So just like I took the domain of the original function, I always want to consider the domain of this. Now, again, it's a 2/3 power, so that 3 on the bottom means it's a cube root. We can put anything in a cube root. Anything works, except one problem. We can't have a 0 on the bottom, so anything that makes that a 0, I'm not allowed to have because it's a denominator. So I cannot have this equal to 0. So basically, x cannot be 1. Every other number works, but 1 does not work. So that does not exist in my derivative. Any other number, like I said, if you plug it into this orange box, you're going to get a number. It may not be a pretty number, but it's going to be a number. 2, 3, 4, 5, 6, 0, negatives, anything works. But if you plug in 1, you'll get an error on your calculator. You'll get an error just because you cannot take a 0 on the bottom. So every number works in our derivative except for 1, which means this is a critical point for our next step. Okay? So just kind of file that away. We cannot have a 1, therefore it's considered critical. Now, what does it mean for the slope? What does it mean for the graph? It can mean a lot of things. You'll see in a second. All we need to know right now is it's a critical point. It's one that we have to worry about. Okay, now remember the second part. It was the first part before. we want to set the derivative equal to 0. Okay? So, don't look at that right here. Let's look at this. I want to set that equal to 0. Well, when you have a fraction equal to 0, the only way a fraction is equal to 0 is if the numerator equals 0. Well, our numerator is -1. No matter what number I plug in for x, I'm always going to have a -1 on top, so I'm never going to get anything that makes this equal 0. So what they wrote here was that the derivative cannot equal 0. Well, the reason is let's set it equal to 0, but when you solve this, like maybe I'll multiply both sides by this, I get -1 is 0, I get no solution. Now, all that means is nowhere is your derivative equal to 0, so you're never going to have a horizontal tangent line. You're never going to have a place where our graph has a slope of 0. But it doesn't mean we can't increase or decrease. So that's what our next part is. When they talk about these partitions here, you take all of your critical values, and those are going to be your borders. So if you go back a couple slides, remember where the derivative is equal to 0, that was a critical number right here, and we checked around it. Well, we don't have that critical number this time, but we do have a critical number at 1. We're going to check around that. So that's what's happening on this next step. X equals 1, our one point that doesn't exist in the derivative, we want to check both sides of 1. So that's what we're doing. So we take the same derivative right here. We're going to test the number over here, and we're going to test the number over here. Test both sides of the 1. So when I plug in, say, a 0, it looks like I get a negative number. I get a positive on the bottom, but I get a -1, so it's decreasing on the left. When I plug in a 2, I also get a positive number on the bottom, but a negative on top. So I'm decreasing both places. Okay, so our function is decreasing basically everywhere except right there at 1. Okay? Everywhere it's decreasing except for x equals 1. So we want to try to look at how this looks. Now, they're not going to show you the graph yet, but I'm going to give you a little preview. Oh, they do have it right there. I'm sorry. No, no. I was going to pull it up on Desmos, but... okay, sorry. I got to go through all this real quick. Okay. Not only do we have lots of slides here, lots of pieces on each side. So, how this graph looks, this is what's going on with this graph. Okay, you notice it's decreasing all the way up to here, and then for a split second, it actually has a slope which is undefined. That's why the derivative did not exist at 1, is because right here, there is no slope. The tangent line of this red one does not exist. The slope, I'm sorry, of this tangent line does not exist. So it's decreasing, decreasing, and then right here for a split second, it's like going to infinity, so it's not considered increasing nor decreasing. So, but then it picks back up and it still continues downward. So that's what we're saying is it's decreasing for all of x. Now, at this point, it has a vertical tangent. You could make the argument that it's still continuously dropping here. It didn't get flat like the other graph. They say it's not defined. Whether they say it's decreasing or increasing is kind of a weird thing because it's a vertical line. I've always gone with the idea that it's decreasing, and then right here it stops for a split second and then continues to decrease again. Okay, now what's ultimately going to matter to you all? They're going to ask for these different pieces, but they want to make sure that you can figure out the graph. Can you get to the final graph? All of these steps, just keep in mind, are helping us get to not just a graph, a sketch. We're going to get to a nice graph. We're going to be able to graph all these in a very precise manner. Okay, so now we're back to our function. I'm going to point out in the original function right here, we have a domain of the original function where x cannot be 2. Everyone see that? So it exists everywhere, but it doesn't exist at 2. So does that mean there's a hole? Maybe. Does that mean there's an asymptote? Probably. But something, we just know there's no point there. So just to point out, if the point doesn't exist, you definitely cannot get the derivative at that point either, because there is no point. All right, so let's see where we go. We rewrite, this is just a rewrite of the function. Now we're going to find the derivative. So I'm going to make sure you see how this derivative came about. Remember the power rule. Bring the -1 out front, decrease the power by 1, so -1 becomes a -2. So my derivative is this. It's negative 1 over x minus 2 squared. Now, again, just kind of repeating my same process, I'm looking at the domain of this. Same thing, you cannot have a 2. So that kind of falls in line with what we had in the function. Not a surprise. But we always want to check because there may be other points that don't exist. But this is important because now, remember, the next step is set it equal to 0. Well, when you set it equal to 0, we have the same problem as before. When you set this derivative equal to 0, it never happens. There are no points where you can get a 0. So we say, okay, there are no other critical points, but we do have a critical point at 2. So we're going to do our sign chart and check all around the point 2. Okay, so here's my sign chart. Take a second to kind of look that over. And every time you're testing around, in this case, 2. So pick a point to the left. I would pick a 0. Plug that 0 into the derivative, not the original function, but into the derivative, and see what you get. And you see I get a negative. Plug in another point on the right side, 3. When I plug it into here, that also comes out to be a negative. So that tells me my graph is decreasing on the left of 2, it's decreasing on the right of 2. And on the right, you actually see what the graph looks like to kind of explain what's going on here. Our graph is decreasing, and then it hits a point that doesn't exist, and then when it picks back up, it's still decreasing. Even though it looks like it jumped higher, look at the behavior of the graph. It's always going downward. Even though it restarted up here, it never technically increased. So you're looking at not what are the y values, just looking at the picture. It's decreasing the whole way except for right there. Okay, so now we talked about this. High point, local maximum, all this stuff. And you see here's a nice little quick summary here. Here's a place where slope is 0. Here's a place where slope is 0, and here and here. What are maximums and minimums? You see here, we get a a high point at C3, this one. We get a high point at C6, and that's a special case because technically when you look at the tangent lines, it goes up, 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 and then down, 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 but it never actually gets to be a horizontal tangent. It's a special kind of case. Here's a case where our graph is sort of disjointed, and you'll hear me talk about in a minute, smooth graph. Smooth graph is one where, as you can see, it's nice and contoured, no rough edges. Here's like a jagged edge. That's not smooth. Here's a jagged edge, not smooth. Here's one as well. So unique things happen at these, what I call not smooth edges. Okay? And then so we have our low points at C2 and C4. And the main key I want you to see is the derivative, when it's equal to 0, tells you certain things that are going on. It gives you some hints of where to look for these high and low points. Okay? So, local maximum. I'm going to go back to this picture here. This is a maximum right here, but it's not at C3. But it's not the highest point. It's much higher on the left. It's much higher right here. But a local maximum means within its immediate area, it's the highest point. So in this little short area, this is the high part of a mountain. Same with this one being a local minimum. It's the low part of its area. So in the immediate area, just think hills and valleys are considered local maximum, local minimum points. Okay, so local extrema, extremum, getting a little Latin here. These are just kind of, that's a generalized form. It could be either local max or min, all right? So turning points is another nice, probably more better English phrase. Turning points are what we have here. All right, so I'm going to jump around a little bit and talk about what's going on here. And you can see what's going on. If you've noticed your graph is decreasing and you have a special a slope 0 right here and then it's increasing, just think, my graph goes down and then goes up. That's got to be a local minimum. Okay? Because it's dropping, it hits the point, and then it turns around. That's a minimum. You kind of see what's going on right here. It's decreasing, then it's increasing, and you know that's a special point there. Well, that point's got to be at the bottom. That's your local minimum. Right there. Okay, same thing the other hand. If you have a graph that is increasing, and then it hits the point C, whatever our x value is, and then it decreases, you'll see it's increasing, then it's decreasing, and then that point right there is going to be a local maximum. Okay, so when the sign does not change, then it's not going to be a max or a min. So if it's increasing and then continuing to increase, not a max or a min. When it's, you can see right here, it hits this, and then it goes there. Notice that's not a max or a min because it's not the highest point of the area or nor the lowest point. Okay, so it's neither. And that happens sometimes. And then same thing when it's negative and negative, you see it's decreasing and then decreasing again. That's also not a max nor a minimum right there at that middle junction point. Okay, so we talk about horizontal tangents. A lot of this sort of goes back on what it's saying. This is how you're able to get these points, how we can get the vertex, or in the case of a more complicated graph, we can get all the important points. Now, although this won't be a maximum or a minimum, it is going to have some importance later on, okay? It still is going to mean something, any kind of values like this. Now you get one of these weird ones where you'll find when we solve for the derivative, it's where the derivative doesn't exist. So we check both sides, it's a negative and it's a positive. Well, guess what? That point might exist. The derivative may not exist, but the point will. Okay? So that is actually considered a local minimum. Same thing like this would be considered a local maximum. Okay, then we get these other weird ones where we have, we graphed one of these earlier where the slope is undefined at that point. It's neither a max nor a minimum. Okay, so sorry, let's go back to this problem. So we have a function, x cubed minus 6x squared plus 9x plus 1. We want to find the critical numbers of f. We want to see if any of those are local maximum or minimum, and then we want to sketch the picture. If we have A and B correct, that really lays the foundation, gives you framework for how to make the graph, and that's the whole goal here. So first part, let's look at where the domain doesn't exist, and we want to see where it's equal to 0. So we've got to check both of these. Where does it equal 0, and where does it not exist? So first step, let's find the derivative. 3x squared minus 12x plus 9. So when I set this equal to 0, this is an old polynomial from algebra. I set it equal to 0. I factor out, I factor again, and I find two critical numbers of 1 and 3. So I kind of went through those slides quickly. I just want to make sure you see those. Please feel free to pause, obviously, anytime as I'm doing this stuff. Okay, so now, those are critical numbers. We have to, and they point out here, the derivative exists for all real numbers, all x. Go back to my derivative right here, 3x squared minus 12x plus 9. There are no restrictions on my derivative. There's no points that don't exist, so therefore, these are my only critical numbers, 1 and 3. So now, I'm going to find out, we've got a part A, now we want to know local maximum minimums. Well, we have to do the partitions, the sign charts again. So remember, here's 1, here's 3, and you pick x values around 1 and 3. So if I go in the middle, the easiest one to pick is 2. Plug in 2 to my derivative. Now, the derivative is gone. Remember the derivative right here? If I was to plug in 2 right there, I would get 12 minus 24 plus 9, which would give me, I think, a negative 3. So that's how I know the middle section is decreasing, because I got a negative number for the derivative. When you plug in something like 4 or 5 or 10, plug that in the derivative, you're going to get a positive derivative, so it's increasing, the function's increasing. When you plug in a negative, you're also going to get a negative, or I can plug in 0, I'm sorry, right here. Back to my derivative, if I plug in 0, I get a positive 9. That means the derivative is positive. My function is increasing here. Okay? So now, knowing this from what we just talked about, we can tell that this point right here, it increases, it hits this point, and it decreases. Therefore, that's a relative maximum. Then the 3, it decreases, it hits the 3, and then it increases. That's a relative minimum. So we know maximum at 1, minimum at 3. Those aren't the actual coordinates. Remember, those are just the x values. All right, so they just want to know the local maximum minimums. Now we're going to sketch the graph. So one of the first things I would do is I would plug in the 1 to the original function to get the value of that function. So when I plug in 1 here, I get 1 minus 6 plus 9 plus 1. That looks like I get a positive 5. Yeah, right here. 1 comma 5, and we already said it's a local maximum. Then plug in 3 here. It's going to take a couple more steps, but when you plug in 3, it looks like we get a positive 1. So 3 comma 1 is a local minimum. And notice it has nothing to do with the y value. It has to do with the fact that our graph is increasing, and then it hits this, decreasing and increasing, and then all we have to do is sort of fill in these blanks. We're going to learn soon. Next level is we're going to go find intercepts. That'll give us even more information. But these 2 points, these that look like vertices, these are the most important. Graph, and then go, follow the table that we just found. Our graph needs to increase up to 1, x is 1. It needs to decrease from 1 to 3 and increase after. And that's exactly what our picture does. Increase, decrease, increase. Okay? So now, a couple things. This is good general information. When you have a polynomial, I know this looks ugly. This is messy right here. But just think, it's a polynomial where the highest power is some x right here. What they know is the degree is going to be greater than 1. Let's see, polynomial function degree greater than 1. It has at most n x intercepts. Okay, so when we talk about intercepts, I know there's a lot of information up here, but just think of it as this is how many terms. This is supposed to be an n, by the way. I'm sorry, it's again another typo from Pearson, but whatever your highest power is, that's the maximum number of intercepts you can have. So remember, see, we have a graph of power of 3. At most, my graph can hit the x-axis 3 times. Well, it hits it once, but if this is a little bit lower, it would hit it once and then again and again, but the most you can hit is 3 times. So whatever your highest power is, whatever your degree is, that's the maximum of the x-intercepts. Okay? Now, for the extrema, the highs and the lows, you can have at most n minus 1. So go back to this graph with a power of 3, a degree of 3. Notice there were at most 2 extrema, local maxes and mins. At most, you have 2 of them. So if this had a graph, a power of 7, at most we'd be having 6 of these maxes and mins. We may have less, but that's the most you can have. And that helps you so that you don't get out of hand. Your graph doesn't go everywhere. Okay, last couple ones here. We're going to talk about economics. Again, something to fit our course here. We have a rate of change of the price of eggs over a 70-month period, and E is the function, T is the time, and we want to know where is the price of eggs, rising or falling, and sketch the possible graph of ET. Okay, so they kind of already gave us this right here. I'm not sure why it says sketch it, but we're going to talk about what we have right here. This might be a premature one. Yeah, just jump around here and see what's going on. Okay, from this right here, you can see you don't even need the derivative, but we know that the graph is increasing all the way up until about 30, and then after 30 it's decreasing. So if we were to find the derivative, it would be increasing up to 30, and the derivative would be decreasing after. Okay? So a couple other things here. That's the rate. We know what the numbers are right here, so notice there's different things. Let me go back here. Rate of change, okay? So this is the price. So we're clear here. And we're going up to a 70-month period here. E of t is the price. Okay, now I know what's going on. It's really pixelated on my screen here, but this is the derivative. This is what they're telling us. So they kind of gave us backwards information. They're giving us the derivative of this, okay? And they want us to come up with a graph of the actual function. So what this is saying, what I gather from the derivative is we're not changing, we're negative right here. Okay, so the derivative, let me start this over. Your derivative is negative here, here and here. So that's how we were able to say the graph is decreasing. The original function is decreasing right here and decreasing here. And then our original graph is increasing up here. It's what's the value of the derivative. Okay, so I'm going to focus on these points. Because at 10 and 50, when t equals 10, our derivative, e prime of t, is 0. What this means is this is critical. Same thing when t is 50. These are critical points. Okay, they could be local maxes or minimums. We don't know yet, but they're critical points. We have to find that out. So that's what we gather working backwards from a graph is you want to first see where, and again, this is the derivative that they're showing us. Where is our derivative equal to 0? It's equal to 0 at 10 and 50. Okay, our derivative is under, it's a negative value here, which means we're having negative slopes. Here it's positive slopes, so we're going to use that information and say, well, we know it's decreasing, increasing, and decreasing. That's kind of the summary we get here. So that's what they're talking about. So now we graph this here, and so we know the price of eggs is rising because the slope is positive in between 10 and 50. The price of eggs is dropping between 0 and 10 months and after 50 months. So if I can draw this and kind of make a picture, and they tell you a lot of the redundancies, this is the picture that we're looking at right here. Basically, here's my horizontal slope at 10 and 50. Okay, the places that we said were critical. And remember from the earlier graph, we knew leading up to 10, our graph was decreasing, and then it hit the 10, then it's increasing here, hit the 50, and it's decreasing again. So it's kind of a, I'm not going to say it's the greatest first example here of the word problems, but it gives you an idea of how this all comes into play. Now, when I jump to the homework here, you're going to see it's going to be a lot better. But this is just our first example. Okay, so let me get rid of this, and then I want to pull up your homework and let's talk about these problems. Okay, so as you can see here, go back to the MyMathLab. Let's look at where we're at here, and let's get into our assignments and start looking at 4.1 now, which is part of week 9 now, correct? Yep. So here's our homework. We're going to find this is going to be a trend of problems going to go up and down. We're going to have a handful here, but let's just start looking at what we got. I think we're going to go up to number 31 is what we're going to get to. So I'm going to do all these here just to show you how they are going, what I expect to. Okay, so let's start with number 3. Give you an example of this. All right, so they asked you, the graph of the function is shown to the right. Identify the intervals in which f of x is increasing. So they don't give you numbers, but here's A, B, C, D, E, F, G, H. We want to know where is it increasing. Now remember, at all the high and low points, it's neither increasing nor decreasing. Okay, that one, that one, that one, that one, that one. But we just want to know, where is our graph going up? Well, it's definitely increasing between B and C, and it's also increasing between D and E, and it's increasing this whole way between F and H. So that's what I'm looking for. I think that's it right there. And that's all you need to do on this first one. They just want you to be able to visualize a graph, and are you able to see that? And are you able to just look at the picture and understand what increasing and decreasing means? So don't worry when you see a lot of homework problems. You're going to get some of these where they're just kind of getting you used to the process. Okay? So now let's look at number 7. Match the graph of f with the correct sign chart. Now remember, this is the actual function. Make it a little bigger there for you. There's the function, and you can just look at this and say, okay, I can tell by looking at it, it's increasing all the way up until it hits x equals 1. Then at 1, it's decreasing and going all the way down. Okay. Now, one of the things here you can see here is it's increasing to decreasing. It's going to be one of these two. They both, notice the sign charts say the same thing. They both have a positives and a negatives, but the difference in the middle is here, on D, the derivative is 0. On this one, the derivative doesn't exist. Now, the cases where the derivative didn't exist, remember, were the jagged points or those vertical lines. But this is a nice standard graph where if you look, the tangent line, if I was to draw this tangent line right here, it would actually be a horizontal graph, a horizontal line, I'm sorry, right there. That is a slope of 0. That's why that's a 0 right there. And that's why D is our choice. The one above is when you're going to have a graph. You kind of remember we had one that looked like this. And right here, the slope is not defined. That would be this B choice if that was the case, okay, if we're talking about that. So that was the distinction of the two. Even though they both have the same sign charts, they're taking it a step further and asking, well, what do you get? What do you have? And that's our one right there. Okay, pick the one with a 0 when the slope is actually a 0. All right, so let's jump to number 11. And trust me, they're going to get a little more difficult. The first ones are just kind of warm up to get you used to the information. So for the function below, we want to find the derivative, and then we want to go and the partition numbers, and then the critical numbers. Okay, so first off, here is my function. Now the first step I have to do is I want to rewrite the function. So notice this is still the function, but it's this right here. Okay. Now, you could use the quotient rule as well. It'll work the same, and I'm not going to say one's better than the other. They both work. But I'm going to bring that -1 up front, and my new power is -2. This is my derivative. Chain rule, because it's x plus 3, the derivative of the inside is a 1. I don't have to make any modifications. So my derivative is -6 over x plus 3 squared. Okay, so now that's the first question. Negative fraction, and some of you may be wondering, do I have to put the negative in the front or do I put it on top? It does not matter, as long as you have exactly one of them. All right, so there's my derivative. We're good on that one. Now we want to find the partition numbers that we're going to use. So in this case, all right. All right, just want to make sure I've got it right. I generally would do the critical numbers first. Looking at this, though, let's look at our derivative right here. Now, remember the rule is, what numbers, where does this equal 0? And when you set that equal to 0, so I'll do that on the next line. If this is equal to 0, as I told you, the only time you can get a fraction equal to 0 is if the top is 0. Well, there are no variables on top, therefore, there are no points here, no x's. Okay, so when I'm making, and I think the partition is kind of awkward because we're not there yet, but I'm looking for critical numbers. Like I said, I like to do this part first. I'm not sure why they did it out of order. But now the other part is, where does this function not exist? So you got to ask yourself, what x's can I plug in there that mess it up? The only problem I have is I can't have a 0 on the bottom, so I'm not allowed to have a -3. Okay, so now technically that's a partition number. I don't know if they're counting this differently, so I'm going to type in that -3. Yeah, and it works. Okay, and the critical numbers are basically the same thing. It's all the numbers that would work. So whether you had, oh, what did I miss here? -3, -3. Okay, I get you. Sorry. Let me go back here. Okay, let me get rid of all this. So definition-wise, they're technically all critical numbers. The -3 is a critical number. I know we defined that earlier as any number that x doesn't make the function, the derivative work is a critical number. Any x that makes it a 0 is also a critical number. In this case, though, what I'm going to say is, I'm guessing this is what they want. I don't know if I care for this, I'm going to be honest with you, but for the homework, yeah, this is what they want. They're counting a critical number as something that's going to eventually come up and become a relative max or min. So let me pull up the slide. I'm going to show you. I'm worried that sometimes the person who wrote the slide didn't write the power or didn't write all the other stuff here. But going back to that critical number stuff, show you the actual definition. Okay. I have a fear here. Yeah, technically, both are critical numbers. Okay, so here's what I want you guys to think of, and we're going to do this on the next homework problem. Critical numbers. Let me do the problem again just to show you what we have. Okay, so we have our partition number as we can't have a -2. We got that right. Now, when I typed it in here for critical numbers, it technically should be a -2. I just want to read what they're going to say here. Oh, okay. I know what we're talking about now. Why this is not the case. Okay. So we have to do the partition around everything. The reason this is not a critical number, and I overlooked one important fact that I told you to do earlier, but I neglected on this one example here, was if you look at the domain of the original function right here, that point does not exist. Okay? That means it's not critical. It can't be a maximum, it can't be anything because the point does not exist right there. So you have to use it when you make your partition because you're going to test, our sign testing chart right here. You're going to use it as a partition. However, when it comes down to it being called a critical number, technically it's not called a critical number because it can't exist in the original function. Now, if there's a point that doesn't exist in the derivative but can exist here, it's a critical number. But if it doesn't exist here, we throw it out. And that's why we had to pick that one right there. We had to go with that to get the answer. So that hopefully that clarified the definition. And we'll see that again in a second. So not to worry. Oh, did I have multiple parts? Oh, yeah, we did all that one. So let's look at number... Is it 15? Okay, now at number 15 here. So, find the intervals where it's increasing and where it's decreasing and the local extrema. All right, so first step, look at your domain. Domain's going to be all real numbers, so I don't have anything to worry about here. Let's find the derivative now of this function. And just so you know, I'm only rewriting it just so it can be a little bigger on the screen because I know it's kind of small. So we get our derivative, we get a 3x squared plus 8. And now, looking at that domain, it's also all real numbers, so I don't have to worry about anything, any other kind of critical points, any other issues, partitions or any of that stuff. Okay? So now, let's see here. Now we set it equal to 0. And we're going to solve. Okay, but you're going to notice when you bring this over and you divide by 3, you get -8/3 equals x squared. If I was to square root both sides, notice I get a square root of a negative number, which means there is no solution. So we had no points that didn't exist. We had no points that were, where it made the derivative equal to 0. Which means we have something interesting going on. We have no critical points possible here. But we can still make a table. Normally we would do a critical point here and we would test both sides. But now, guess what? It's all one big region. We just have to test one time. Okay? Test one time to see what we get. And either everything's going to be positive or negative. Test any number in our derivative right here. Let's find f prime of, I'll just pick 2, for example. And you see in that derivative right there, we get a positive number, which means we are increasing everywhere. This entire graph is increasing. So the graph is increasing where? Well, I'm going to answer that. It's every single point. It's going to be from -infinity. Oh, can't do that here, sorry. -infinity up to positive infinity. That's where our graph is increasing. Where is it decreasing? Well, it never decreases. And let's see, they solve our mess here. Oh, and they ask you, what's the local maximum or minimums? Well, if our graph is always increasing, we will have no minimums nor maximums or anything else. It has no local extrema. And just to be clear how that graph looks, so let me go back 1 second here. How the graph of a cube function looks, remember, it's going to be something like this, going up and up like that. It just never goes down. So this is the case. We'll see it's increasing the whole way. It never stops. There's no maxes or mins. And that's what we have here. Okay, so that's what we have here. And that's it for this problem. That was all the 3 parts. Okay, so now, where are we at? Number 19. Find the intervals in which the function is increasing, decreasing. Same thing, but it's a different graph, a different equation. So we have f of x equals 9. Add 9, let me do that. 9 plus 8x minus x squared. First thing, you don't have to write it down. Just think of what's the domain, okay? So if you have the domain, it's all real numbers. We don't have to worry about anything. It's only when things are not in the domain that we just have to make a note of it. So here I find the derivative and I get 8 minus 2x. Again, check the domain, no problems. So I set this equal to 0, solve for x, and we get x equals 4. That's my only critical number. So now I got to do my little chart right here. Let's test around 4. Now remember, again, you're testing in the derivative. So when I test a number, let's just say I test 1. When I plug it in here, I get a positive. When I test something like 5, and I plug it into the derivative again, I get a negative. So we are increasing here, we are decreasing here, which tells me at this point, which exists, this should be a maximum, because our graph is going up, it hits the 4, and then it goes down. So let's see what they ask. Where is it increasing? So it's increasing everywhere from on the left of 4. So that's going from negative infinity up to 4. And remember, it's a parenthesis around the 4 because at 4 you're neither increasing nor decreasing. So make sure you don't include the critical points in your answers for increasing, decreasing intervals. Okay, this one, where is it decreasing? It's decreasing everywhere from 4 onto positive infinity. All on the right side. Okay, now we pick our graph, and then remember, the graph, the point actually exists. Everything exists here. This pointed thing right here, that's a case where the derivative does not exist. It's that awkward jagged side. Here is our case where the point actually exists, and there's our graph. Okay? All right, so let's look at some more while I erase this. Look at number 23. Okay, on this one, we're going to use a graphing calculator. So I'm going to use Desmos again, like you're all allowed to do. And we want to approximate the critical numbers of the function to 2 decimal places. Let's see how well we can get that. And then find the intervals in which it's increasing, decreasing, and the local extrema. All right, so approximate the critical values. Now notice they've already kind of given you some choices here, so we have something to work with. But let me pull up this, see what I can find here. Okay, so 1 second. Usually I have Desmos up, I just forgot to put it up this time. Okay, there we go. So, graph this function right here. We have f of x. And you don't even need to put the f of x. You can just go with the actual function right there. Minus 5x to the third plus 7x. Okay, so now you see, number one, let me just kind of review a couple things. Remember the highest power is 4? That means at most we can hit the x-axis 4 times. Remember we had that little rule earlier? Sure enough, we hit it exactly 4 times. Okay? We also know that we can have, at most, remember subtract 1 from that? At most we can have 3, excuse me, 3 maximums mins, and we have exactly 3 of them right here. Okay, so the question they're saying is they want to know, let's go back, of the critical numbers. Okay, so our critical numbers are all the places the derivative is at 0. So let's see where we're at here. So we have this negative 0.632, and all we're looking at is the x's. So there's our negative 0.63. All 4 of these choices have it. Okay, our other one, our second one is up here, and it's at 0.76, so round that to 0.77. All of them have that as well. And now our last one is not the intercepts, but way down here. I should have zoomed out before I went down. But we have this value at 3.616, so round that to 3.62. And you can see those are my critical points right now. Now, the only one I would consider is look at this C. Everything's the same except they have this 4.73. Why they have that is, I have no idea. It looks like they just picked a random point to see if people were guessing, but it looks like it's only going to be B. Okay? So now part 2 is saying the function's increasing. So let's look at the graph. We can see it's increasing between this point and this point, and then it's also increasing from this 3.6 all the way up forever. And zoom out if you need to. It just keeps going up and up and up. So my first place it's increasing is going to be between that negative 6.63 and the 0.77. So I'm going to start with that. Negative 0.63 all the way up to 0.77. And then I want to make a second interval notation, and that's where's our little union symbol right here. Oh, they wanted us to use the comma to separate our answers. Okay, let's go back. Not sure if I like that idea of a comma, but we'll do that here. And back to our graph. Remember, we were at 3.62 all the way up to positive infinity. Okay, and there it is. So normally I would put a union sign in between these two interval notations, but they actually said to put it as a comma. Now, I'm curious, I'm going to purposely do a union symbol on this next one just to see if it works. But now decreasing, remember it's everything from negative infinity up until that first point. So negative infinity up to the negative 0.63. And then, like I said, I'm just going to use the union to see if they mark me wrong. And then it's also decreasing from this critical value of 0.77 all the way up to the 3.62. Okay, now that answer is technically correct, but the fact that they said use the comma, they might not like it. Yeah, they didn't like it. So, like I said, I just wanted to test the system so you guys don't have to make that mistake. Now we put the comma and we're good. Okay, and last one, which of the following is true? All right, function has a local minima, let me pull up my graph, at negative 0.63. That looks right. That's a local minimum right there. It has and at 3.62. Well, at 3.62, yep, that was this other one way down here. X values were 3.62 and a local maximum at 0.77. So that looks like it's exactly correct. Okay, but before I submit it, I still want to look at the other ones. Local minimum at 0.77. Well, we already have this highlighted. 0.77 is a max, so that's out. B is not good. D is not good already because we have the local extrema. There are 3 of them. And the third choice, local minimum at negative 0.63, that's good. 0.77, nope, because that's a maximum. So they just switch these two. A looks like it's going to be our choice. And we're good there. Okay? So that's it on that one. Like I said, use Desmos or any kind of graphing tool that will definitely help you out here. All right, so we'll look at number 27 now. The graph is continuous. That means there's no gaps, no holes, nothing, no jumps. Use the information to sketch the graph. All right, so a couple things here. You have to know what the language is that they're saying. They tell you f of negative 7 is 49. Remember, that's the original function. All of these in this first box, these are actual coordinates. There's a coordinate negative 7, 49. There's a coordinate 0, 0, and a coordinate 7, negative 49.
Okay? Then they tell you, let's go right down here. The function is increasing from negative infinity to negative 7, and it's increasing from 7 to infinity. Then they tell you actual derivative points. The derivative of negative 7 is 0. The derivative of 0 is 0. The derivative of positive 7 is 0. So let me start with those. Those are all extrema. Those are all critical points. Something's happening there. And since the graph exists everywhere, those are going to be maxes or mins. We'll figure that out in a second. Then it's telling us where it's decreasing. So I want to put all these together. So forget the graphs. I just want to look at what they tell us. So let me do this. We'll come back to the choices in a second. Just based on what they've told us. All right, I'm going to fill in it. It's like I'm filling in a puzzle. We have the point negative 7, 49. So there's actually a point. I'm going to make it a big point so we don't miss that. There's a point at 0, 0. And then there's a point at 7, negative 49. So let me get rid of that line right down here. Okay? So that takes care of this first box. We got rid of all that stuff. Okay? So I'm not going to cross it off and get rid of that, but just to show you, we've done this box. Now, let's do this second box. They tell you at negative 7 is a max or a min. So I don't know what it is right now. It's going to be one of them because the derivative at negative 7 is a 0. Same thing with this one. This is going to be a max or a min. I don't know yet, but I'm just writing this here. And same thing with this one. That's a max or a min, a local max or min. Okay? So now let's look at that. That takes care of this for now. Let's look at the other part. It's increasing. So right here, it's a positive slope between negative infinity and negative 7. That means it's going to go up to that point. Our picture. It's also going to go up from 7 to that infinity. Okay, that's what we get right there. And then our fourth box means it's a negative slope, a negative derivative, meaning it's decreasing between negative 7 and 0 and 0 and positive 7. So you see all these lines I put? We actually have the picture. It's going to look something like this. Get rid of all this. Oh, I got rid of too much, sorry. But we have a good idea of how this picture looks, and now I can go back and answer some questions about this. It's increasing all the way up until here, then it hits it and turns around. It's decreasing, hits that, and is increasing. This is an approximation of how our graph looks, a very good sketch. Okay, so now, looking at some things, I know this is a maximum just because it was increasing up to it and then decreasing after. I know this is a minimum because it was decreasing until it got there and then it increased. In the middle, it was decreasing and then it was decreasing again. You know what that means? It means it's neither a maximum or a minimum. It's none of those. Okay, so that middle point actually is nothing. And I'll show you how the picture looks. I'll refine this in a second. But this is what we know from all the information. I have a max, I have a min, and now I can try to fill in our graph here. Which graph looks the most like this? Well, if you look at all of the three up there, only one of them is even close. It's this B right here. Okay, and you see if you kind of zoom in a little closer, what's going on is in that middle spot, because it has a 0 slope, what actually is happening in the middle there is the graph comes down and it sort of is like a chair and it keeps decreasing, but for a split second it goes flat. That's why you had a slope of 0, why you have a derivative of 0. But that's this picture B right here. Okay, and that was it for this question. That's all they wanted. So did you have to do all this graph? No, you could have eliminated some other ones, but I like to just go with a fresh sheet of paper and just start graphing or plotting or indicating every little bit they tell us. And it's kind of like a puzzle. You have to understand what this means. When they tell you f of negative 7 is 49, they're giving you a coordinate. When they tell you f prime of negative 7 is 0,
they're telling you that it's a zero slope tangent line right there. So it's a max or a min or something. When they tell you derivative is greater than zero, derivative is less than zero, it's just another way to say the graph is either increasing or decreasing along those indicated regions. Okay, so let's look at number 31 and see how good and bad this one is. Okay, so they give the graph of the function in this little box, which I'm going to zoom into in a second, and use the graph of this one. So I'm going to make it big. All right. Okay, so find the intervals in which the derivative is greater than 0 and the intervals which the derivative is less than 0, and the values for the derivative is equal to 0. Sketch the graph. Okay, so start with the zeros. I know my derivative is 0 at all the local maxes and mins. Here, here, here. Those are all the places we have a 0. Okay? And it looks like it's pretty clear. Critical points, x equals -8, 2, and 9. So now I just have to look at where are things increasing or decreasing. Well, it's increasing here, it's decreasing here, increasing here, and decreasing here. So to kind of summarize it here, where is the derivative increasing? Well, it's going to increase. That's another way of saying increasing. It's increasing between -infinity and -8, and also between, excuse me, 2 and 9. Where is it decreasing? Where is the derivative less than 0? It's everywhere from -8. I'm sorry, that was a -6. I read that wrong. Sorry, go back. -6. -6 is what that point is right there. Okay? So everywhere from -6 up to 2, it's going to be decreasing. And everywhere from 9 to infinity, it's going to be decreasing. Okay? So I wanted to write all those out because now I have to get rid of my picture. And where is it greater than 0? Where is it increasing? Okay, so everywhere from -infinity up to -6, we said. And again, they wanted the comma in between the intervals. And there's our first answer. Where is it the derivative less than 0? Where is it decreasing? It's everywhere from -6 to 2 and from 9 to infinity. There's my increasing. Where is it equal to 0? At -6 and 2 and 9. Oops. That's it for number 31. Nope, sorry, no, that wasn't it. We have one more, fourth part. Sorry, we have to sketch it. Okay, now, sorry. We have to sketch, I'll leave some of this up here. We have to sketch what we think the derivative looks like. Now, it is awkward when you look at derivative. Just think of it. We have all these answers here, so I'm going to clear everything out because we have everything written. Okay, so remember, when the derivative equals 0, it equals 0 at -6, 2, and 9. So look at my pictures. I want to see the graph, the derivative graph, hitting the 0 at -6, 2, and 9. And I think it does. 1, 2, 3, 4, 5, 6. It hits here at 0, and this 2, and this 9. Okay, and just pick a couple more here. At -6, and at 2, and at 9, the graph is at 0. Same thing here. -6, 2, and I assume that's 9. And this one, -6, 2, and 9. So those are all right. Now the other part that's awkward is, where is the graph increasing? It's increasing all the way up to -6 and then also between 2 and 9. These pictures aren't going to look like you're increasing. These are pictures where the graph is above the x-axis, above the x-axis. So between negative infinity and -6, it should be above the axis, and sure enough, it is. And then between, where were we at here? 2 and 9, it should also be above, and notice it was below. All right? This derivative means it's a negative number. We are not in the negatives between 2 and 6. Sorry, 2 and 9. It's got to be something above the graph. So, look at each of these. It's above the graph here. It's above the graph here. It's below. This looks like it's a good answer. This one, same thing. It's below the graph up to -6, so that's not going to be it. And this one, same thing. It's below the graph here, so out. B is our only choice. Don't get too caught up on if you get this last part wrong. I'm going to tell you this is probably the graph of your first derivative is going to be one of the least important things we need right now. So like I said, don't get caught up on this. If you get it wrong, don't spend an hour doing it. Just skip it. I want you to make sure you can do the other parts before we go on. Okay? So I think we got one. Yeah, that was the last one for section 4.1. So I'll stop it here. We've had a long video. I know there's a lot of material. You should be able to get up to number 34, essentially. No, sorry. Yeah, 34 on your homework. So work on those. You should be good to go. I'll record a second video and send it out to you shortly for section 4.2. So go ahead and get on that. If you have any questions, like always, let me know. Have a good one.